Well, back here at the Cave of Science, and we're going to look at the review of the plate tectonics test. The first question, you have three different diagrams here of a subduction boundary, and it says give a possible explanation, explain the differences in angle subduction. As we talked about many times in class, it's the difference in densities, and we know the oceanic plate has greater density, and the greater that density compared to the continental plate, which is less dense, you have a steeper angle of subduction. So the middle one has the greatest angle, so this difference between densities would be the greatest. The top one would be a little bit less difference, and the bottom one would be a lot less difference in densities. And that's also why you get the volcanoes farther inland, when you have very, very small difference in densities between the oceanic plate and the continental. Excuse me. Oops. Don't want that. There we go. The second question, we're looking at almost a verbatim of what was off the lecture. Draw the movement. Well, we know the material here in the mantle, closer to the core, is going to be warmer. And so warm material will rise as it approaches the Earth's crust. What doesn't ooze out in the diverging boundaries or seeps through as volcanoes and so forth is going to cool and sink back down. So you have this cycling here, which is called a convection current. And we know as the magma rises, it's going to cool, and as it sinks, it's going to start to warm up again. The next question deals with a spreading center, oceanic ridge, diverging boundary. We know the oceanic plate is basalt. It's mafic, magnesium and iron. We did a couple activities. As you move away from the ridge, the ocean floor becomes cooler, therefore it becomes denser, and it becomes older. The average rate of movement somewhere around 5 centimeters per year, and you did several problems, and the answers were within that range. What evidence? That was the whole idea of magnetic reversals. That was the whole activity we did on that. The examples in class illustrate a transform boundary. We used the San Andreas Fault out in California. Continental converging boundary, the Himalayan mountains, the Indian plate smacking right into that Eurasian plate, and the East African Rift or the Red Sea would also work here. We looked at both of those as really they're continental diverging boundaries. Question number 5, what is the rate of movement for plate A or B? Well, we did several problems like this. So here's the ridge here. This is where the magma will come to the surface. So it spreads at the same rate on either side. So we know this would have to be the 0, and we're looking to the point where it's 3.3 million years old, and halfway, half of 300 kilometers is 150, because you don't want to do it all the way across because it's the same things happening on each side. And I give you a little hint, 1 kilometer is 100,000 centimeters, and we know rate is distance divided by time, and everything we did in class was centimeters per year. So 150 kilometers over 3,300,000 years. I should have put years in there and I didn't. And we know there are 100,000 centimeters per kilometer. Kilometers are gone, so we're left with, if we do the math, 4.5 centimeters per year. Pretty close to the average rate. The next question, what type of boundary? Well, it's an oceanic continental, and it is a subduction boundary. And the oceanic feature, when you looked at many of these, at these subduction boundaries, is the trench right in here where this oceanic plate starts to subduct. What causes the ocean plate to subduct? Has greater density than the continental plate. The name and the classification of the rock that comprises the continental crust, it's granite, felsic, feldspar, and silica. The next one on the Hawaiian Islands, very, very similar to the two we did in class. We did the Hawaiian Islands in class, and then the other one we looked at was the Yellowstone area. And these are both hotspots. The first thing it asks you to do, you had to do the graph. And let's see, I don't know if I can rotate this thing or not right now. Let's see if I can rotate it. There we go. And here's the graph. The information was up here. I guess that rotated them all. I guess I'll have to rotate it back. But we have the information up there. This is just a XY graph. And as you can see from this XY graph, it goes in a westward direction. Actually, if you look at this, and we talked about this in class, the excuse me, the movement over the Pacific Plate over the Hawaiian Hotspot, which would be down the lower right-hand corner, because those are the youngest islands, is to the north and to the west. So as you move west in longitude, those are definitely getting older. And let's see, we'll go on here. I'll probably have to go back and reverse rotate this one again. And let me rotate it one more time. There we go. And we're looking for distances here. And we have our key here, 1 centimeter is 43 kilometers. And it's asking you from the instructions from Kilauea volcano to these different volcanoes in the islands. So here's a Kilauea, you know, from Maui, it would be from here to there, from Molokai, from here to there, right up there's the volcano, and so forth. This is the exact same problem we did on our activity sheet. So you get the age, excuse me, you get the distance, the approximate age in years, just write that from the previous data sheet you had. Which is the youngest? Well, if we look here, it's got to be the island of Hawaii. Which Hawaiian island is the oldest? If you're going to use this one here, the oldest one's going to be up there, because we knew the hot spot is where the present volcano is. And so it's moving in a northwest direction. And so Kauai would have to be the oldest. And the islands and their longitude, well, as you can see, as you move west longitude, they get older. What is the inferred age of Nahu? And you can get that from using the graph that you created before. What island does not seem to fit the pattern? Really anything farther west. I kind of let that go a little bit. You could probably have used this one here. Seems a little bit farther west than the direction it's going. As you move away from the Hawaiian island, where the hotspot is, a couple possibilities could have happened here. One, they spent less time over the hotspot, possibly, and also water is a great agent of erosion. Well, it says predict where the next Hawaiian island will form. Well, if you go back up to the map, it's going to form right here, really right in the same spot Kilauea is, or as the plate's moving to the northwest, it's going to move from a southeast to a northwest direction, so it would be right in that area. And calculate the rate. I'll do that right below. Which direction is Pacific Plate moving? Northwest. And we need to calculate the rate moving over the Hawaiian hotspot. And it tells you to use from Hawaii at the Kilauea volcano to Kauai. I hope I'm pronouncing that right. So we calculated our 13.5 centimeters, and we know 1 centimeter is 43 kilometers, so that gives us our kilometers. We know the time, and the time was given on the data sheet. Went from 500,000 to 4.7 million years. That gives you a difference of 4.2. And it's the same problem we did several times in class, and you also did previously on the assessment. 580 kilometers, and again, write million years, write it out as a number. So 4,200,000. And we know there are 100,000 centimeters in a kilometer. Same problem. And as you work it out, actually it was pretty quick, about 13.8 centimeters per year. And that was the assessment. So really, every activity we did really reinforced all the problems on this. So that's it for that. So yeah, I would review this if you plan on retaking the assessment.